Okay, so we start our seminar with the talk of Di Yang from the University of Science and Technology of China. And the title is Large Genus Asymptotics of the Brezin-Gross-Witten numbers. Okay, Di, please.
Thank you very much. Sorry for the delay. So yes, thank you for first. Thank you for the invitation. So today's topic is about the large genus asymptotics of the Brezin-Gross-Witten numbers. So this is a joint work with Jindong Guo, Paul Nobry, and Dang Zagir. Yeah, so let's start with the first, considering a more familiar numbers, a more familiar set of numbers, the Witten intersection numbers. So let G and N be non-negative integers satisfying the stability condition 2G minus 2 plus N is positive, and let MGN denote the moduli space of stable curves of genus G with N distinct mark points. So in 1969, Deligne-Manford introduced a compactification of this moduli space using nodal curves. So we denote this compactification as MGN bar. And we will denote by psi I the first Chern class of the ith topological line bundle on MGN bar. So the integrals of psi classes over the moduli space of stable curves, the MGN bar, are called psi class intersection numbers. So they are also called Witten's intersection numbers because of the following conjecture and theorem. So if we denote, so in mathematics to study many numbers like this, so these numbers are indexed by non-negative integers I1 to IN, and also G and N. So to study many numbers, a way is to introduce the generating function. So we denote by F the generating function of all these numbers. So we use epsilon to track the genus of these numbers and to use Ti1, Tik to the T sub I to track the powers of these psi classes. Okay, so and this generating series is usually called the free energy of these intersection numbers. And if we denote by U the second derivative of the free energy with respect to X is the T, X is just T0. And then Witten's conjecture says this generating series U satisfy the Kotovich-de Vries hierarchy. So in particular, this series U satisfy the KdV equation. So it is this third order evolution equation. So it's non-linear because of this term. And so yeah, it's the famous KdV equation. And Witten also gave the initial value of this solution is given by when all higher time equals 0 is equal to X. So for evolution system, if we have the initial value from this together with this interhierarchy, we can uniquely determine this U. And then to use theory from inverse system, we can determine the free energy. So, so from Witten's conjecture, we can compute, in principle, we can compute all these numbers. So Witten's conjecture was first proved by Kontsevich, and it is now also known as the Witten-Kontsevich theorem. Yeah, so based on the Witten-Kontsevich theorem, since as we mentioned from this evolution PDEs, we can solve all this nonlinear PDE to get a closed solution, to get a unique solution. So, and in particular, with Marco Bertola and Boris Dubrovin around 2015, we solved out this PDE system. So we solved out all these PDEs, and indeed we obtained an explicit formula for all these numbers. So if we denote by Cn the endpoint generating series of these intersection numbers, and from this PDE, so to solve this PDE, we actually use the Lux formalism. So and from that we obtain this explicit formula of this endpoint function in terms of a 2x2 matrix. So this M is a 2x2 tristless matrix, and so yeah, the term, they are all explicit given, and then we consider product of these 2x2 matrices and take the summation over the symmetric group Sn, and from this we get all these endpoint functions. So to use this endpoint function to compute Cn, all the computations are algebraic. So instead of from the PDE, we know that it's somehow we will do some integration, but here everything's just algebraic. Okay, so for example, we indeed compute many numbers. So these are in particular 3-point. So 3-point numbers. So so 3-point means so here k equals 3. So you see already from 3-point numbers, the index is not very high. So still it's like 14, 17, 14 square, 17, and here 20, 21, 22. But the numbers are already very huge. So huge means the numerator contains big primes very quickly. So you see this sub-index is not very high, but the numerators already has big prime. Yeah. So then somehow the question is somehow we have some way to compute efficiently many of these numbers. So we want to study the properties of these numbers. So in particular, in studying the Maser-Rich volumes of moduli spaces of quadratic differentials, Dirichlet-Guirac-Zograf Zograf, and Aggarwal, they introduced the following normalized psi-class intersection numbers like this. So so these are the original psi-class intersection numbers multiplying some factorials. So these are unlike these intersection numbers, which immediately, I mean, very quickly, they contain large primes. So the numerator contains large primes. So unlike these numbers, so these factorials, they do not have large primes, right? So for example, when in the previous examples, when n equals 3, so this d1, d2, d3, they are 20, 21, 22. So here the numerator is just at most some prime smaller than 20, smaller than 20, right? So sorry, smaller than 40 something, 43. But here this is contains huge. I didn't do the so factorization, but just by experiments you can see it's indeed contain very large primes, so much bigger than the factors here. So this normalization is just so didn't change very much the this combinatorial property of these numbers. But it does make an effect. The effect of this normalization is the following. So Deliquak-Zograf storage, they made this conjecture. So for arbitrary positive numbers, C smaller than 2, so this renormalized psi class intersection numbers GDG, it tends to 1 uniformly for this range. So for n smaller than or equal to C log G, and di are arbitrary. So because of the degree dimension counting, the sum of these di's should be 3g minus 3 plus n. So apart from that, they are arbitrary. The range of n is smaller than or equal to C log G. So, right. So so the remark is that for fixed n and fixed d1 to dn minus 1, the large genus asymptotics of psi class intersection numbers were already studied by and also given by Liu and Xu. So as I mentioned, the effect for this renormalized numbers, they make the uniformity possible. Right? So the possible of the uniformity is mainly on this number n. Or on the on the sum of these di's. So yeah. So what I'm saying is that for original psi class intersection numbers, already they have uniformity for fixed n, but for arbitrary d1 to dn minus 1. But only after one makes this proper normalization, we can make it more uniform. And indeed, to study the volume of the moduli space of quadratic differentials, we need this C to reach to 8. So here is for any C smaller than positive number C smaller than 2. This was the original DGZZ conjecture. But later, actually, this C can be an arbitrary positive number. So as long as this C can reach to 8, it can be used to study the volume of the moduli space of quadratic differentials. Okay, so this DGZZ conjecture was first proved by Agarwal and then later independently by Jindong, Guo, and myself by different methods. So Agarwal's proof uses Dirichlet-Valinde relation, or equivalent saying is called Versor constraints. And our proof with Jindong, Guo, we use the explicit formula here to use this trace formula. Yeah, they are also called the determinantal formulas. Right. So so you see here we can show this n can reach arbitrary C times log G. In this range is uniform. So Agarwal actually proves an even stronger result. So he shows that this n smaller than C log G can be replaced by n equals to little o square root of G. And so beyond this, we cannot improve this anymore because there are counterexamples for GDG. Right. So today our focus is on some numbers very similar to Witten's intersection numbers, and also very interesting is called the Brezin-Gross-Witten numbers. So they were introduced by so their partition function was introduced by Brezin-Gross and Gross-Witten in the beginning of 1980s. So so they were originally, the partition function is defined via matrix integrals. So here the integral is, integration is over unitary matrices, and A is a complex m by m matrix. So we denote the numbers. So the numbers, they are Taylor coefficients of log of this partition function with respect to some MIVA variables. And so these Taylor coefficients will be called the BGW numbers. And these numbers so we know that they vanish unless their sum equals G minus 1. So for example, to get some feeling about these numbers, so here they are the first few of these BGW numbers. So again, the BGW numbers, as long as this, when this the sub-index D1 to Dn, when they are not very big, so relatively big, but not very big, already the numerator of these numbers will contain large primes. So which means they are also quite non-trivial numbers. So from just some, for example, from these numbers and from much more data, we immediately say that, observe that these numbers are, so the BGW numbers, they're almost always integers. So we conjecture that they are integral away from the prime 2. So this looks a very simple conjecture, but so far we don't know how to prove this conjecture. It's still a conjecture. Right? You see the numerator here is always powers of 2. Yeah. So for a long time, there are no topological or enumerative meanings for these BGW numbers until recently. So 2 topological meanings for the BGW numbers were found out. So the first one is the so-called integrals of theta class. So these numbers are shown to be integrals of over MGN bar of theta class coupling psi classes. And so they were conjectured by Nobri, first by Nobri, and later with a complete proof by Chidabaram, Gatchafeld, Giacchetto. So here, theta GN is the Nobri theta class. So, and Kazarian and Nobri, they found that the theta class can be represented by certain kappa classes. And this was also later reproved by Jianghao Xu and myself using Galilean symmetry. Right, and the second topological meaning for the BGW numbers is an ELSV-like formula. So ELSV is named after Ekdahl, Landau, Shapiro, and Weinstein. So which means these numbers, these BGW numbers, they are also equal to some, again, some class integral of this, some classes over MGN bar. So here, the psi class entered in this way from the numerator in this product way. And so kappa here, kappa D is again kappa class. So this, so here, sorry, I forgot to ask, yes. So here, lambda Z is the term polynomial of the Hodge bundle over MGN bar. So in this formula, we also have some kappa class, and this kappa class is different from Kazari-Nobri kappa class. So yeah. So these kappa class are different from the theta class. So this was discovered and proved by Qingsheng Zhang and myself. So yeah. So from these formulas, we know that the BGW numbers, originally they are defined as some matrix integrals, but actually they also have enumerative or some topological meanings. So there are also some important rational numbers, and conjecturally they are almost integers. So just essentially they are integers. Right. Okay. So however, either from this formula or from this formula, so to compute these numbers is not very easy because integrals over the unitary group or from this original definition, because the integrals over the unitary group or over the moduli space of stable curves, so they are not algorithmically defined. So so then how do we compute these numbers? So the first way is to use the DVV type relation. So DVV here is Dycraft-Vlind. So in this BGW case, again, we have a DVV relation, a DVV type relation. So they are obtained by Donobre, also several, maybe years, or I don't know, maybe around 10 years or 7 or 8 years ago. So yeah, so the DVV type relation is a kind of recursion. So from the recursion, so here essentially it is if you consider the sum of these the sum, so the sum of the DI, so you can see the right hand side will have smaller sum, and so it is indeed a recursion. So somehow it's a little remark is that it's somehow a little more than a recursion, because there could be several different ways to get the same number. So then I need to show they are compatible. However, so here we have or some original definition of these numbers, and then we show they satisfy, and Donobre showed they satisfy this recursion. Another remark is that this DVV type relation here for the BGW numbers, they are also equivalent to topological recursion. Right. So the second way is again to use the PDEs. So we want to solve the KDV hierarchy together. So instead of, so the only difference between this way, I mean, using this way between BGW and Witten-Kontsevich is the initial value. So the initial value for this PDE system is X for Witten's for the Witten's intersection numbers, and for BGW case, it is known that the partition function is also a tau function of the KDV hierarchy. I didn't give the reference for this result. It dates back to also Brezin-Gross-Witten, and also Mironov, Morozov, Seminov, and also Alexandrov, and also Donobre. So okay, so this so the only change, so the partition function is still tau function of the KDV hierarchy. The only change is the initial value. So the initial value of the BGW solution is given by this 1 over, roughly speaking, is 1 over x squared. So actually, in 1970s, they also, 1970 or 1980s, they also appeared in already this initial value already appeared in Duistma and Grünbaum's study on the bispectral solution to the KDV, to bispectral solution to the linear Schrödinger operator. Anyway, so they have some long history, and so when we solve the KDV hierarchy with this initial value, and we run the same method, the so-called matrix resolvent method from the Lux pair. So we use this method, we get the same type formula. So sorry. So the explicit 2x2 matrix is obtained by Dubrovin, myself, and Zagir, and apart from this, the shape is almost the same with this Witten's. So the endpoint k-point function for Witten's intersection numbers. So here, this formula was also independently found and proved by Bertola Ruzza using Riemann-Hilbert correspondence. So in particular, the 1-point number we have, so here BD B, D1 to Dn are some kind of some renormalized BGW numbers by just multiplying some double factorials. So, and from this, for example, the 1 point normalized BGW numbers is given by this formula. Okay, so from this generating function, so from this endpoint, explicit endpoint function, we can, as I mentioned, if we use this formula to compute the numbers, so the BGW numbers, everything is algebraic. So what we need to do is to compute the residues, right? Because these are coefficients of some low-long expansion, so we just need to compute these coefficients. And by computing the residues, we obtain an explicit formula for the numbers itself. So here, this little a, k1 to kn, they are trace of these 2x2 matrices, and omega. So here, omega are some numbers. So it's still summation over the symmetric group, and for each permutation, we associate some number. So it's some number combinatorially defined. Okay, so it's just some explicit formula. So let's see some examples. For example, for n equals to 2, so this B D1 D2, we have this more explicit formula, and then from this we get actually B D1 D2, the 2-point BGW numbers. They can be represented as just a sum, right? So it's a very simple sum. So here, this FH looks like it's very similar. FH is very similar to the 1-point numbers. So here is a sum of this product of F. And for 3-point numbers, we also have the similar expression. So these are obtained from this general formula. Right. So now let us introduce some better normalized BGW numbers. We call it CD. So D is D1 to Dn, the partition. And so here, the previous normalization is to have this double factorial. Now we also divide by some numbers. And the advantage of this normalization, the first one is that from the DVV type relation, we know that if we add 0 in this partition, then it's unchanged. So which means we can really consider partitions of so these numbers are really labeled by integer partitions with positive parts. So right. So here XD is the sum of 2dj plus 1. Okay. So right. So so we also use GD denote the sum of this the weight of D plus 1. So then we know that this sum is just 2g minus 2 plus n. Right. So now let us give a list of these renormalized BGW numbers CD. So this CD, they are normalized BGW numbers normalization by this simple, as I said, they are essentially some simple factors. So the essential numbers are the primes. So for example, and because of this property, C0D equals CD, we only need to look at partitions, the usual partitions with positive parts like this. So for example, let's consider they are categorized by this G. G is the weight plus 1. So when G equals to 2, there's just one partition, so it's 1. When G equals to 3, there are 2 partitions, 2 and 1, 1. When G equals to 4, there are 3 partitions, 3, 1, 2, 1, 1, 1. So we use some ordering for these partitions. So some lexicographic ordering. So then we look at the yeah.
The denominators are no longer powers of 2.
Oh, the yes, because because we also do the renormalized BGW numbers. For renormalized BGW numbers, we divide by some factorial. After this, because of this, the numerator is no longer powers of 2.
Okay.
Yeah. So from this integral point of view, they are not as nice as before, but later we will see, for example, from this property, they have a better property, and later we will see the main. So actually now we can already see the main advantage for the new normalization. So after we did this new normalization, now instead of look at as a rational number, instead of this, we will look at the digits. So for example, the first one is 0.28, 1250, and now it's 0.2929 and so on, and now it's 0.295 and so on, and 0.299, 0.300, 0.3022. And now here in genus equals to 5, we have 5 partitions, and they are 0.3028, 304, and so on, right? So now we see a very interesting phenomenon. So they are monotone increasing, right? So we see from these numbers, they are monotone increasing. So now we have these conjectures. So the first conjecture is called nesting conjecture. The nesting conjecture is that for any fixed G, so when G is fixed, all these numbers are between this partition, the number corresponding to this partition, and the number corresponding to this partition, to 4 and 1, 1, 1, 1, right? So nesting. So it's a weak version of monotonicity, and the strong version is the we call it monotonicity conjecture. So is the function from partition to rational numbers to Q. Sorry. It is strictly monotone increasing with respect to a certain lexicographic ordering for every G. So here, actually, it was about 10 years ago when Nobry, the story is about 10 years ago when Nobry and Zagier, they were studying these numbers. And they, in the very beginning, they introduced this normalization CD. And yeah, they make this nice observation. Yeah, and yes, so right, they did for many experiments, and they made this conjecture. So here's only some of these numbers. Right. Okay. So motivated from these two conjectures, and also some details of this motivation. Maybe if I have time, I will explain some more motivations later. So, and our first theorem is that all these numbers, they uniformly tends to 1 over pi. So this number 0.3060 and so on. So it will goes to 1 over pi. So this is the first theorem, and so this uniformity is the complete uniformity. So here, for the special case when n is fixed, this large genus leading asymptotic was also obtained by Anna Gachiafeld, Giacchetto, Gregory, and Levansky. So here in our theorem, we achieve to a complete uniformity. So it is even better than here, right? So in Agrawal's case, so in this DGZZ Agrawal case, so here is uniformity is only, so there are counterexamples. So it's only up to this little o square root of g. So here we can reach to complete uniform in N. Right. So let's now consider the proof of this theorem. So right. So as I said, if I will have more time, I will explain some more details about the motivation. So, but this nesting conjecture and monotonicity conjecture, they play a very important role in this to get this statement of the theorem. But I want to say that although we have this this theorem, we still do not have the proof of either, I mean, either this nesting conjecture or monotonicity conjecture. So, in other words, our proof didn't use this. So we are motivated from these two conjectures, but our proof of the theorem will not use either of this. But we for the lower bound we can prove. What I'm saying, we don't have the proof of the nesting conjecture is that we don't have this upper bound, the proof for the upper bound, but we do have the lower bound.
So,
right.
Professor, how, as the genus grows, how can you preserve the partition?
As the genus grows?
Yeah, the genus grows, and you have partitions of G minus 1. And in the statement of the theorem, you analyze, here. Now, how can you fix the, how you can preserve the partition D as a genus?
So uniformly, as GD equals the weight of D plus 1, as so for any D, right? So we don't have any requirement for N. So so here uniform is as the D, the weight of D plus 1 goes to infinity.
Thank you.
Yeah, okay. So, right. So let's now consider the proof. So what we do is we will use, in the proof of the, this DGZZ A theorem, Gujarat storage and Agrawal theorem. In the proof of that theorem, Agrawal, he introduced some technique, involving this so-called random walks. So here we use part of his techniques and we improve that. So let's see. So in the big direction, we will use DVV type relation. So DVV type relation written in terms of CD, in terms of this renormalized BGW numbers is given of this form. So there are some linear term and also some quadratic term. So, and from this and also by induction, to get the lower bound, it is not difficult. So first we can prove the lower bound by induction. And so the difficulty is to get the upper bound. So for that, what we do is first we define a function called theta chi n. So this theta chi n is when xd is this sum of 2di plus 1. So when all xd equals x, so we consider the maximum of this cd with xd equals x, and we call it theta xn. And then we also introduced a number theoretic function f chi n, so by a recursion. So this recursion is given in this way. So here, this is the recursion, and we put the initial data to be 1 over pi for x from 1 to 7 and n equals 1, 2. So so number theoretic, so here, which means this it's a function of 2 variables, and each variable belongs to positive integers. So yeah, so we define this f chi n by this recursion. And then this is an explicit definition. We can show that this is kind of an elementary function. So this function is monotone increasing with respect to n. And also we have an upper bound for this function f. The upper bound is, for example, we can get to 1. Right. And so our lemma says, so for x, any chi and also any n smaller than or equal to chi over 5. In this case, this number theoretic function goes to 1 over pi uniformly, so in this range. And so to prove this, because this function is kind of elementary defined, right? So we can actually get a closed formula for this function. So the closed formula is that it is 1 over pi plus this rational function plus sum from 8 to chi. And so here the coefficient p, so the functions p and chi is given as the Taylor coefficient of this elementary function. So, and then to analyze this f chi n, we just use the residue theorem to estimate the coefficient, the Taylor coefficients, to get this uniform asymptotics. Okay, and so the property of this f chi n is that we can prove that this f chi n gives it gives a upper bound for the theta chi n, and from this, essentially from this we can again use this DVV type relation. So for n is big, is bigger than chi over 5. What we do is that we iterate this inequality t times. So t equals to this 5n minus chi plus 1 divided by 4, the integer parts. And so this integer is the first time when n minus t, so after sufficient many this iteration, the first time when this is smaller than or equal to chi over 5, and so that we can use this estimate. Right. So then we obtain this this after the iteration we obtain this inequality, and it tends to 1 over pi. So yeah, this gives the proof. Right. So here I want to say that in original Agrawal's proof, so because the normalization in Witten's case is not as, so here we have the complete uniformity, And if we use this normalization, the function here is better. And also the coefficient is better. So in Agrawal's case, we don't have this better shape for this recursion. Because of that, we need to introduce some random walks. So you see here is essentially just so you have some, you can consider as a story that you have probability 2/3 to go to the left and the probability 1/3 to go to the right. But since here we have a better shape because of this complete uniformity, right? So the uniform is complete in N. So because of this, I mean, it's because we could get a better statement. So here we don't. So here we don't need the we don't need to use these random walks. Yeah. Okay. So right. So let us now turn to the second theme of this study. Is about the structure of BGW numbers. So I'm a little slow. So I need. So the structure. So first is that using the explicit formula, we can show the ratio of C lambda G minus 1 minus weight of lambda divided by CG minus 1 is a rational function of G. And so here we can describe all the possible poles, of this rational function. And we get, so here Q lambda G, it's a polynomial with almost integer coefficients in G. And so here, yeah, so all the possible poles can be described. So from this, we can immediately prove that the renormalized numbers for any fixed partition lambda, we can get this asymptotics, so full asymptotics, right? So in the study of Witten's intersection numbers, Guo and myself found that for each k, the coefficient of 1/g in the full asymptotics for Witten's intersection numbers is a polynomial of n and multiplicities of the arguments. So, and the argument only involves from 0, 1 to 3k/2 minus 1. So this is called the polynomiality conjecture for large genus. And in the study of BGW numbers, we found that the same phenomenon also holds. So if we consider range of these partitions, we will get also some structure for the CK lambda. And now they are polynomials of n and multiplicities of 1 to k/2 minus 1. So both of these conjectures were proved by NR and his collaborators. So there is a further discovery. So we already know that each coefficient is a polynomial of n and multiplicities. So by a careful look using the DVV relation, we find that so this coefficient actually they are so the sum is unchanged if we increase n by 2 and decrease g by 1. And because of this, we deduce that if we write this asymptotic, the full asymptotics, as a function of x inverse, x is 2g minus 2 plus n, then these coefficients will be independent of n. Right. So, and moreover, we also not just write this full asymptotic in terms of x inverse, and we also normalize again these numbers by this factor. If we divide by this factor, we can kill all the constant part of this coefficients. So now they are polynomials of multiplicities with zero vanishing constant part. And so, right. Yeah, so this is the polynomiality statement. And the proof is, our proof is also different, completely different from the proof of Ennard and his collaborators. So here we use the DVV type relation, and Ennard and his collaborators use the resurgence method. Right. So yeah. So I will just omit the proof. So now let's look at the application to the Painlevé-2 hierarchy. So the Painlevé-2 hierarchy, the definition of the Painlevé-2 hierarchy, I will be very quick. So for example, the first equation in this hierarchy is the Painlevé-2 equation. So, and we can use the Lana-Marguerite recursion or some similar recursion to get the whole Painlevé-2 hierarchy. Okay, so there are some nonlinear ordinary differential equations. So we will focus on the case when the parameter in this Painlevé-2 equation or hierarchy is 1/2. So in this case, we can easily show that there is a unique formal solution Vx of this form. Yeah, and so our theorem says that the coefficients of this formal solution is tends to 1/π multiplied by this factor, and as n goes to infinity. So for the case when d equals 1, so when it is the Painlevé-2 equation, this theorem can be obtained from a deep result by Eads and Kapayev using the Riemann-Hilbert analysis by computing the Stokes constants. And so now we achieve a new proof. And as far as we know, the cases with d bigger than or equal to 2 are new and are also difficult. So the proof is just to use our theorem 1. So it is from string equation, from the string type equation, we can show that generating series of this c d to the power n. So d to the n means ddd, so n copies of d. And this c d to the n, this satisfies the dth member of the Painlevé-34 hierarchy. And due to the celebrated result of Clarkson-Joshi, or for when d equals 1 by Ablovitz focus, we know that we can perform a kind of Murat type transformation to transform the Painlevé-34 hierarchy to the Painlevé-2 hierarchy. And the rest of the proof follows from theorem 1, because somehow we made all this CD to the n uniform. So in the BGW numbers case, and to get the uniform 1/π asymptotics. So this gives all this all the asymptotics. So of course so in the transformation we also need to use the so-called rapid divergence series. Yeah. Okay. So sorry. Can I have some more minutes?
Yes.
Thank you. Thank you. So I will just speak some more about combinatorial properties of BGW numbers. So the monotonicity conjecture says that the normalized numbers CD with partitions D, so this D1 to Dn of a fixed length are smaller than those of greater length. So in this monotonicity conjecture, because we have this lexicographic ordering, so if the numbers are of the same length, in particular they are smaller than they are bigger than of smaller length numbers with smaller length, and bigger than this and smaller than numbers with greater length. So then we can draw a picture about these numbers. For example, when G equals to 40, so there are 3, 1, 1, 8, 5 partitions of So it's G minus 1 of 39. So there are 31,185 normalized BGW numbers, and we want to draw all these numbers in some range in the range of these numbers, and it turns out that so the numbers with the same length, they are actually much closer to each other than the numbers of different length. So they are, of course, because of the monotonicity conjecture, the intervals, they become right, they didn't intersect each other, and but actually because of when they have the same length, they are much more close to each other. So the interval, the 39 interval of all these numbers, the 39 intervals look like 39 points. So because so the red are the intervals, but they look like a point. So we can give a precise description of this phenomenon, of this interval, but these are still conjectural. So we can give a precise size, asymptotic size for this interval. Right. And a second observation is that so what happened if all the parts are large? So in the monotonicity conjecture, it says so the coefficients in the full asymptotic, they are polynomials of multiplicities with it is important now, it is with vanishing constant term. So then if all these parts are large, which means all these polynomials ck in the full asymptotic, they all vanish. So they rapidly tends to 1 when d goes to infinity, right? For example, the error of 1 minus this C100 to the 10, it is this C hat is still renormalized 1. So C tends to 1 over pi, C hat tends to 1. But they're actually very, very close to 1. So there are 285 digits. So 0 of 0. So right. So we want to give the exponential asymptotic. So because the full asymptotic already it does not it didn't give the, so we can refine, we can give a to make a more careful look. So this is an exponential asymptotic. So it's exponential decreasing, right? So yeah. So but this is still a conjecture. Yeah, thank you. I stop here.
Okay, thank you very much. Any questions?
I have some questions, Maxim Kazaryan. The first one is the following. I have seen the following observation. You mentioned DVV type relations which are quadratic.
Yes.
Yeah, this type of relations. And this relation has linear terms on the first two lines and the quadratic term on the last line. And we have seen the following observation, that if you just remove the non-linear term, the quadratic term, if you just consider the linear terms and redefine the number according to this linear recursion, then they have the same asymptotics. Have you seen such observation for these BGW numbers?
Yes, I think from the right. I think already from that the BGW numbers for this should be similar. Yes, because this argument. So let's look at some similar cases. So this Painlevé-2 equation. In this case, so they involve some particular BGW numbers, right? So in this case, also the phenomenon, the phenomenon about this asymptotics up to the constant part, up to the constant factor, they are not difficult. So again, some arguments to using just the linear term already can help to deduce. But the difficulty for these numbers is the final constant is cannot be deduced from this argument.
That's right. I have another question. So all your analysis is based on the closed formulas that you mentioned for the correlation function B or C. And my question is that we have derived with my co-authors another kind of closed formulas for the correlator function. Do you know how to relate the two formulas?
So which formula? Sorry, which formula are you mentioning? This one?
This one, yes. For instance, this one, and we have another. It looks differently, but just the same numbers with the same generating function. We have a different formula for the same generating function, also a closed formula, which.
Are you mentioning that this instead of 2 by 2 is a scalar double series? So it's this A. The formula, some kernel, right? It's some Bessel kernel. Instead of the matrix, it's a scalar, but it's double series. That formula?
Yeah, but still, well, I will probably will discuss it another if there will be a chance. So I would like really to relate the two formulas because both are, in opposite to topological recursion, both formulas are closed, but they look slightly different. So it would be interesting to relate them. Yeah, thank you. And still another question: is it possible that you share the slides with participants of the seminar?
Which to share the slides? Yes. I will send to Sasha Burdiak.
Yeah, if you send to the organizers the slides, and we'll share it. Thank you very much. It will be very useful. Yeah.
Thank you.
I have a question about Painlevé-2 hierarchy. You mentioned that the diff equation of Painlevé-2 hierarchy has a solution of some form. Why is this solution interesting? Why?
Yes. So for the for the Painlevé-2 case, they are studied by Itz and Kapayev. So I think in the Painlevé, there's also the analog of this in Painlevé-1 case. In Painlevé-1 case is proved by Kapayev. So these numbers, so these solutions, for example, in Painlevé-1 case, they are also related to some analytic solutions, some tree-truncate solutions. But in both cases, in Painlevé-1, in both Painlevé-1 and Painlevé-2, of course, for us, is that these solutions, the coefficients, are related to the BGW numbers or to the Witten-Kunsevich numbers. So in the Painlevé-1 case, it relates to Witten-Kunsevich numbers with all powers equals to 2.
Okay, thank you. Maybe also another probably very simple question. When I look at these Witten-Kontsevich intersection numbers, tau d1, tau dn, and if all di's are greater or equal to 2, then all these numbers are between 0 and 1.
Yes.
Okay, and is it obvious that, okay, I think the fact that they are positive is more or less easy, but I'm curious about the fact that they are less than 1. Is it easy to observe?
Yes, this we need to check. Yes, it's a very good observation because you see there are many of these limits. They did to some renormalized numbers. There are some upper bounds, some lower bounds. There are a lot of studies on this, but for your observation, one needs to check if this after this normalization, if the previously known results can lead to your observation. So it is not but one needs to do some exercise. So there's possibilities is still new.
Okay, thank you very much. Okay, are there any other?
Will you please return to slide number 11?
Sorry, I didn't get the question.
Slide number 11.
Sorry, the numbers.
Can you go to slide number 11?
Yeah, here is the initial data for the KBV hierarchy.
Mm-hmm.
Does it allow one to write out the topological recursion curve for the BGW numbers?
Very small.
Yes, there is a topological recursion. It's given by Du and Nobry, and later one can consider an even better way. I don't know. Which means one can consider some so-called generalized BGW. In that case, there is a cohomology field theory and some standard correspondence to topological recursion. So yes, there is a cohomology field theory and also a topological recursion for the generalized BGW theory.
Okay, thank you.
Okay, if there are no further questions, then let us thank Dee again.
Thank you.
Thank you, Dee.
Thank you.
Thank you. So sorry in the beginning, I was figuring out this Zoom.
No problem.
Okay.
No problem.